Assalamu alaikum wa rahmatullahi wa barakatuh. This is chapter 12, Electromagnetic Forces. At the end of this lesson, we're going to be able to recognize the nature of the electromagnetic force, to state Laplace's law and characterize the electromagnetic force, explain the role of electromagnetic force in the functioning of speakers. Before we start, consider the following machines that we use in our life or we have heard of before: fan, loudspeaker, DC motor, or the electromagnetic brakes in the train. Have you ever wondered how it works? Actually, its functioning is based on the electromagnetic force. Through this video, we are going to define and characterize this force. To investigate this force, let's study the following experiment. We are going to use a DC voltage battery of electromotive force E, a switch K, a rheostat, a metallic rod DC that can rotate around its end D, and the connection wires. Finally, we use a source of a uniform magnetic field B vector. First study. We're going to close the switch K in the absence of the magnetic field B, where B is 0. Note that the motion of the rod DC is the aim of our study. So we noticed that the rod DC didn't move. We recorded the result and moved to the next study. After that, we closed the switch K, where B field exists and it's perpendicular to the plane of the figure directed inward. We noticed that the wire is deviated by an angle alpha from its vertical position to one position due to a force exerted on the rod CD. To be sure about this direction of motion, if it is constant, we move to the third study where we reversed the direction of the current, keeping the direction of the magnetic field the same inward to the plane of the figure, and then we closed the switch. The result was astonishing. The rod is deviated to the direction opposite to the previous deviation, but with the same angle. We can say now that the direction of the force that is exerted on the rod is affected by the direction of the current. However, this is not enough to make a full study. So we reverse the direction of the magnetic field to become outward. We notice that the rod is deviated to the opposite direction. What can we conclude now? The force that is resulted from the existence of the current traversing the wire in a magnetic field is directly affected by the direction of either the current or the direction of the magnetic field. This is related to the direction. What about the magnitude? We decrease the value of the resistance of the rheostat, which leads to the increase in the value of the current, since R and I are inversely proportional due to Ohm's law. We noticed that the angle of deviation of the rod increased, which means that the force is increased. We increased also the magnitude of the magnetic field for a given value of resistance. The angle of deviation also increased. What does that mean? It means that the magnitude of the force is increased. So what is the conclusion then? We say then the force F is proportional to the intensity of the current I and also to the magnetic field B. This force is called electromagnetic force or Laplace's force. As a conclusion for our study, we can say that the simultaneous presence of an electric current I and an external magnetic field B creates an electromagnetic force or Laplace's force F. So, what is Laplace's force? It states that any conductor of length L traversed by a current of intensity I and immersed in a uniform external magnetic field B is subjected to an electromagnetic force F vector. What are the characteristics of this electromagnetic force? Starting with the magnitude, it is I, L, B, sine alpha, where I is the intensity of the current traversing the conducting wire, B. The magnitude of the magnetic field L, the length of the conducting wire placed in the region of this magnetic field and traversed by this current I. L vector is the rectilinear element oriented in the direction of the current. Alpha is the angle made between L vector and B vector. In SI unit, F is in Newton, I in ampere, B in Tesla, L in meters. Note that if sine alpha is 0 where B and L are collinear, then the force is 0. The direction of the force F. To understand this direction, first you should know that B vector and L vector forms a plane. F is perpendicular to this plane such that it is perpendicular to B vector and perpendicular to L vector. Whatever the angle between B and L is. To indicate the exact direction of this force, we are going to use the right-hand rule. In this rule, we let the thumb, the pointer, and the middle fingers of your right hand make right angles with each other. Put the thumb in the direction of L vector, the pointer in the direction of B vector, and then the middle finger gives the direction of F vector. Then the direction of F is stated as the perpendicular to the plane formed by the wire and the vector B given by the right-hand rule. It's good to talk about an example. Consider a conducting light rod Mn of length L carries current I directed from N to M as in the figure. The rod may slide without friction along two conducting rails X, X prime and Y, Y prime. The region between the rails is within a uniform magnetic field directed inward to the plane of the figure. The rod will move to the left, then the characteristics of the force are. The point of application is the midpoint of Mn immersed in B. Direction F is perpendicular to the plane formed by B vector and L vector given by right-hand rule to the left. The magnitude F is I, L, B sine alpha, where here alpha is 90 degrees, then it is just I, B, and L. Application 1. Indicate in each of the following cases the direction of the electromagnetic force according to the right-hand rule. Pause the video after each figure and guess the direction. In the first figure, I is upward, B is inward, then F is to the left. The second one, I is upward, B to the left, then F is outward. Third figure, I is downward, B is inward. By right-hand rule, F is to the right. Fourth figure, I is to the left, B is inward, F is downward. The fifth figure, B and I are parallel to each other, then the angle between them is 0. F is 0. Excellent. Now, I is to the right, B is outward, then F is perpendicular to them, downward. The last figure, F is inward. Now, example on the effect of an electromagnetic force. In the adjacent figure, we have two horizontal conducting rails placed parallel to each other and are connected to the terminals of a DC voltage battery of electromotive force E. A conducting rod AD that can move perpendicular to the rails. And finally, the two rails are placed in a region of a uniform magnetic field B vertically upward. If we close the switch, current traverses the circuit and the rod starts to move across the rails. To catch the idea, let's make a side view for this setup and study the motion of the rod. In the side view figure, we can see that the rod was at rest before closing the switch, where there is no current in the circuit. Why is that? Because the rod is affected on by the normal force and the weight only that are vertically opposite to each other, then their sum is 0. When the switch is closed, current traverses the circuit. With the existence of the magnetic field, a Laplace force exists in the circuit, and the rod then moves under the effect of this force with a direction that can be predicted using the right-hand rule. Let's solve application 2. In the adjacent figure, we have two parallel conducting rails 10 cm apart, connected to the terminals of a DC voltage battery of electromotive force E. A conducting rod Mn can move perpendicular to the rails. The whole setup is placed in a uniform magnetic field B of magnitude 0.1 Tesla. The question is, knowing that the rod is traversed by the current of intensity 0.2 ampere, determine the characteristics of the electromagnetic force F exerted on the rod. First, the point of application is the midpoint of the rod Mn. The direction, it is perpendicular to the plane formed by Mn and B vector. Using right-hand rule, it is directed to the right. Finally, the magnitude of F vector is I B L sine the angle alpha, then it is 0.2 times 0.1 times 0.1 times sine 90, since I and B are perpendicular to each other, and finally the answer is 0.002 Newton. At last, it's good to mention an application that depends on the Laplace force in its functioning, which is a loudspeaker. Based on the idea that electric current and a magnetic field external both makes an electromagnetic force, what happens on the loudspeaker? When an alternating voltage U of a frequency F is applied between the terminals of the coil, an alternating current I of same frequency F traverses the coil. The coil is then submitted to a force F parallel to the axis and directed alternatively to the left and to the right. Being fixed to the coil, the membrane vibrates then with the frequency F, producing a sound of the same frequency F. Note that the loudspeaker doesn't work with direct current, since with one direction of current, no oscillations will occur in the coil, and so the membrane will move to one direction only with no oscillation on the membrane. The sound will not be transmitted. This is the end of this lesson. Please take notes, study them well, and thanks for your attention.